So, good morning, dear students. Again, today we are going to deal with some important sections, multiple sections we have for the discussion today. We have solid states, we have periodic classification, we have surface chemistry, and we have isolation of elements. They're all different big chapters. Let's see how far we can go ahead with the discussions. So we start with our first discussion is our solid state. As you know, the entire discussion in the solid state is with crystalline solids, and this crystalline solids, according to the scientist Auguste Bravais, it is of 7 types. So entire crystalline solids is segmented into 7 types of crystal system. They are called as Bravais lattices. And among 7 types of crystal system, the one which we are going to discuss, or that is the part of our syllabus content, is the cubic crystal. We have cubic, we have tetragonal, we have orthorhombic, we have triclinic, we have monoclinic, we have rhombohedral, and we have hexagonal. These are the basic 7 types of crystal system which is there according to Bravais. And the part of the discussion is crystalline solid, that is a cubic crystalline solid. Why? Because cubic crystal is very convenient to discuss because of its arrangement. The edge length are same, ABC if I say, and the angles between the faces, that is alpha, beta and gamma angles, are also same, which is equal to 90 degree. So that is the reason that the cubic crystalline solid is of more discussion as compared to other ones which are tetragonal, orthorhombic, triclinic, monoclinic, rhombohedral and hexagonal. Now if you see the arrangement of the lattices points in cubic, I have given the number over here, that is 3, 2, 4, 1, 2, 1, 1. 3, 2, 4, 1, 2, 1, 1. What does it number means? In cubic we have 3, that is called SC, BC and FC. 2 means SC and BC, 4 means SC, BC, FC and EC, 1 means SC, SC and EC, SC and SC. So together if you count up 3, 2, 4, 1, 2, 1, 1, if you count up together, it comes out to be 14 types of arrangement. So Bravais said there are 28 possible combinations in which it can be arranged, but later on under study it was found that 14 of them actually exist and 14 of them they do not exist. So the one which exists, it has been given over here in the form of these numbers. Okay, so there are basically 4 different types here. One is SC, one is BC, one is FC and one is EC, which is called end centered. That end center is not that common for discussion. Mostly we discuss for SC, BC and FC. Now as I told you, SC cubic crystalline solid is very convenient and easy for our discussion because of the edge length and the angles. A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to 90 degree. See, out of this 7, 4 you can easily remember without any problem. The other 3 you need to remember them because of the difference in the edge lengths and as well as also on the angle part. So first one is A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to 90 degree. That comes as a cubic. In case of tetragonal, one of the edge lengths are not equal. So A is equal to B, not equal to C. Angles are equal to 90 degree. In the third one, both the edge lengths are not equal. A is not equal to B, not equal to C. The angles are equal to 90 degree. And the fourth one, as a triclinic, neither the edge length nor the angles are equal to each other. So A is not equal to B, not equal to C, and alpha is also not equal to beta, not equal to gamma, not equal to 90 degree. So this is what we have talked about, the arrangement of edge length and the interfacial angles. Next we come on to the types of the lattice point and their contribution to the unit cell. If you talk about the atom present in the corners, see already you have studied in your first PU and you have studied in the second PU part of it. So basically it is just a revision segment which we are doing here. Type of the corner, type of the lattice point. If you talk about the corner ones is having the contribution as 1 by 8. If you talk about the face center, the contribution will be half. If you talk about the edge, the contribution is nothing but 1 by 4. it is 1 upon 4, and fourth is the body center, which the contribution, the entire contribution of the atom present in the body will be taken up. This is very important for the calculation, the questions which is done, like, atoms are present in the corners, they are also present in the faces. Can you determine the formula of the crystalline solids, like those? So corner is having 1 by 8, face is having 1 by 2, edge is having 1 by 4, and body center is having 1. So this is what we have discussed in the first page we have talked about. Let's go on to the second discussion. There are basically two types, primitive also, and we say non-primitive in the discussion over here. When we say primitive, the atoms are present only at the corners, and that is called as SCC. And we have non-primitive, we have corners also, as along with corners we have face, that is called FCC. And non-primitive, we have corner plus body, that is called as BCC. Okay, so primitive as well as we have non-primitive. So primitive is just the simple cubic unit cell, that is called as SCC. Non-primitive can be FCC and can also be BCC. Now, first of all, if you are talking about a cube, what are the arrangement of the atoms present? In the cube, there are 8 corners. Okay, there are nothing but face centers. If you talk about, there are nearly 6 face centers. Okay, 4 of the walls and 1 on the top, 1 on the downside. If you talk about the body center, it is nothing but 1. If you talk about the end center, it is nothing but 12. Similarly, if you talk about in a cube, the face diagonals, they are nothing but 12. And the body diagonal, if you talk about, that is 4. So face diagonal is nothing but 12 and the body diagonal is nothing but 4. So what is the body diagonal? Body diagonal is this particular line which I am talking about from here to here. This is the body diagonal. So like this, we have 4 body diagonal, and the face diagonal, if you talk about, so this is nothing but the face diagonal. So like this, if this is one face diagonal, this will be another face diagonal. So nearly we have 12 face diagonals. We have 4 body diagonals, and edge that is present at the edge corners. Edge centers we have 12, body center we have 1, face center we have 6, and corner we have 8 total as an arrangement. Let's come on to the simple discussion of the SCC. Now if you see the SCC right now, which is over here, there are 8 atoms at 8 corners. If there are 8 atoms at 8 corners, if you talk about this particular atom over here, got it? If you talk about this particular atom, you know already the contribution of the atom present at the corner is 1 by 8. So 8 into 1 by 8 is equal to 1. And what is the relation between the edge length and the radius of the atom R? So if you see the relation between the edge length and the radius of the atom R, very simple it is. It is like this. This is the arrangement where it is this cube. Actually, the atoms are present in this format. So this are closely aligned with each other. 4 on the downside and 4 on the top side. So this is a radius. This is a radius. And the edge length will be what? A is equal to 2r. Whether you take from this direction, whether you take from this, whether you take from this, whether you take from this, A will be equal to what? 2r. And that is the edge length and the radius of the atom relationship. So as we know, the unit cell content, what is unit cell content? That is nothing but Z, which is equal to nothing but Z is equal to 8 into 1 by 8, which is equal to 1. Why 1 by 8? Because the contribution is 1 by 8. And how many atoms are present at the corners? 8. So unit cell content comes out to be 1. Edge length, I have told you, A is equal to 2r. So with this, we can talk about nothing but one thing called as packing fraction. What is packing fraction? Nothing but what is the total volume of the atoms divided by the volume of the cube. So what is the total volume of the atom? That is nothing but 2 into 4 by 3. This is nothing but Z. Z into 4 by 3 pi r cube. What is the value of Z in case of SCC? That is equal to 1 into 4 by 3 pi r cube upon A cube. A is equal to 2r. We are just putting it here. A is equal to 2r. So with this, we can find out the value of the packing fraction, and then comes as pi by 6. And this pi by 6 is nothing but 52%. So mean to say that 52% of the space is occupied. So rest of the space is void space, which is nothing but 48%. So 48% is a void space. Not a good packing, because nearly, if you see, half of it nearly half is the void space. So this is about simple cubic unit cell arrangement. Everybody, I hope you have understood it. Let's go on to the next point of discussion, which is nothing but body centered cubic unit cell. So if you talk about BCC arrangement, that is called as body centered cubic unit cell, this is okay. One more thing if you talk about in the earlier case, that the nearest neighbor concept. If this is the corner atom we have, then what is the nearest neighbor of this corner atom? The nearest neighbor of this corner atom is this one, which is nothing but edge length A. Okay, this is the nearest atom. Okay, nearest neighbor, if you can say. The next nearest is nothing but, if this is A, this has to be root of 2A. So this is nothing but called as a next nearest, which is along the face diagonal. And if you talk about the next to the next nearest neighbor, that comes along the body diagonal. So this is from here, okay, till point here, this is called root of 3A, which is called as next to next nearest. So if you talk about in case of SCC, the nearest neighbor is nothing but A. This is nearest neighbor. Second is the nearest to the next nearest is root of 2A, which I have told you along the face diagonal. Next is next to next, that is nothing but root of 3A here, which is along the body diagonal. So this is what we have talked about. Let's come on to the next discussion now. If you talk about body-centered cubic unit cell, this is the arrangement of the body-centered cubic unit cell. Along with the corners, we have in the body center also. Earlier there was only at the corner, so the atoms were just touching each other. Now one atom has to go into the body. So in order to accommodate that particular atom in the body, the atom of the corner has to be little far away from each other. So this is about the particular thing which I was talking about, that they are little far away from each other. This is far away, all these are far away, and one body center will come over here. This is what I'm discussing. So this is all the corner atom, and this is nothing but the body diagonal. If you say this and this is the body diagonal. So if this length is A, got it, or this length is A, then this will become what? Root of 2A. And if this becomes root of 2A, this is nothing but A, this will become root of 3A. So the body diagonal, if you talk about the entire body diagonal, edge length is root of 3A. So this is the body diagonal where you can see this root of 3A is equal to 4R. Why? Because this is a radius R, this is the radius R, and this is the radius 2R. So R, 2R and R, that becomes 4R. So root of 3A is equal to 4R. But if I talk, my dear students, what is the nearest neighbor in case of BCC? So the nearest neighbor in case of BCC will be from here till here. From here till here, this will be the nearest neighbor. And if this is entirely root 3 is equal to 4R, so this will be root 3A by 2. Root 3A by 2 will be the nearest neighbor, and this is R and this is R. So 2R is equal to root of 3A by 2, that is the nearest neighbor. I hope you understood it, everybody. So this is the nearest neighbor. And if you talk about the next nearest neighbor, this is nothing but entirely, if this is nothing but, this is A. This is called as next nearest neighbor. And if you talk about next to next nearest neighbor, see, this is the chapter deals with visualization. So you need to visualize the three-dimensional arrangements mostly in your mindset, and then you can talk about the arrangements. Okay, so this is what we were discussing right at the point. Okay, if you talk about next to the next neighbors, if you talk about, so next to the next neighbor, what will be the arrangement? This is nothing but root of 2A. This is next to next. And if you talk about next to the next to the next, this will become root 3A is equal to 4R. So dear students, keep this thing in your mind. So whatever I have discussed right at the point, okay, related to all these things, which is nothing but related to the nearest neighbor. The nearest neighbor is nothing but root of 3A by 2. The next nearest is A. Next to next is root of 2A, A root 2, and the next to next is nothing but root of 3A root 3 is equal to 4r. So this is very important. They will ask in the examination in case of BCC the nearest, next, next to next, and next to next to next nearest. So as far as the unit cell content is concerned, that is nothing but Z, which is equal to 8 into 1 by 8 is equal to 1. Body center contribution is 1. Total has been taken as 2. This is called as Z unit cell content. So as far as relationship between the edge length and the radius of the atom is concerned, it is nothing but root of 3a is equal to 4r. So when root of 3a is equal to 4r, we can put it packing fraction PF is equal to z into 4 by 3 pi r cube upon a cube. What is the value of z? It is nothing but 2 into 4 by 3 pi r cube upon, what is a? A is nothing but 4r by root 3 to the power 3. If you calculate it, this will come as root 3 pi by 8, and root 3 pi by 8 calculation if you do, that will come as 0.68. So the percentage occupancy in BCC is 68%, while the rest, is unoccupied, that is 32% is the space which is left up. So if you compare with SC and BCC, the most efficient arrangement is BCC. Why? Because of the more percentage of occupied space. Let's come on to the next one, which is a point of discussion, which is called as the FCC. This is FCC. Along with corners, we have atoms at the face centers. So this particular contribution, this is a face center, this is a face center. All these colored ones which I am talking about, these are nothing but face centers. So if you talk about corner, if you talk about the arrangement, this is nothing but the edge length A. Okay, this is A, this is A. So if this is A, this is A, this is root of 2A. Got it? So how this arrangement will be there? So this is nothing but the atom which is present at the face centers. Face center. So if you talk about the face center entire, whether you talk about this, whether you talk about this, one on the same thing. This is entirely face center. This sphere is present at 2r. This is r and this is r. That is what I have shown you here. This is nothing but 2r. This is r and this is r. So what will happen? This is nothing but root 2a is equal to 4r. This is the face diagonal. Root 2a is equal to 4r. If root 2a is equal to 4r, then 2r will be equal to what? A by root 2. This is nothing but called as nearest neighbor. Nearest neighbor is a by root 2. Next nearest neighbor will be a. This is the next nearest neighbor. And if you talk about next to the next nearest neighbor, that is nothing but root 2a is equal to 4r. So in case of FCC, the nearest neighbor is a by root 2. Why? Because this from here, this distance, this one from here to here, this has been taken as a nearest neighbor. Half of the face diagonal will be taken as a nearest neighbor. Next nearest will be like this, A, and next to the next is along the entire face diagonal, which is root 2a is equal to 4r. Okay, next come on to the contribution. Since the atoms at the corner contribution is 1 by 8, so I'm taking it as 1. And the atom at the face contribution is half. I'm taking it 6 into 1 by 2 is equal to 3. So totality, if you see, the value of Z comes out to be 4. So in case of FCC, the unit cell content is equal to 4. Okay. Now next come on to the edge length and the radius of atom. So simply as I said, face diagonal root 2a is equal to 4r. This is the relation between edge length and the radius of the atom r. Packing fraction, if you talk about same to same, you need to do PF is equal to, instead of Z you need to put 4 into 4 by 3 pi r cube upon 4r by root 2, because 4r by root 2 is the edge length A. So this is root 2 pi by 6. What is the value? Root 2 pi by 6, whose value comes out to be 0.74, which is nothing but 74%. So 74% of the space is occupied, while rest 26% of the space is unoccupied, which is called as a void space. That is a percentage vacant space, 26%. Now if I come on to the efficiency of the overlapping, efficiency in terms of packing, I need to say that the most efficient packing is what? FCC, then comes BCC, then comes SCC. So this is the order of the packing, dear students, please remember. Okay. So this is what we have discussed about the primitive and the non-primitive type of combinations, that is SC, BC and FC. Let's come on to the next point of discussions over here. Let's talk about in the simple questions which if I deal with. The question says that in a cubic crystal, atoms A are present at corners. Atoms A are present at corners and atoms B are present at face centers. The formula of the crystalline solid will be very simple, you know that. Atoms at the corner, what is contribution? 1 by 8. So basically there are 8 atoms. 8 into 1 by 8 is equal to 1. Therefore it will come as A. Face center contribution is half. 6 into 1 by 2 is equal to 3. So this formula comes up as AB3 is the formula of the crystalline solid. Now what we are doing is a deviation of this particular question from this part. If one corner atom is removed, what is the formula of the crystalline solid? So basically if you remove one corner atom, still 7 are there. What will be the contribution? 7 by 8 only. So 7 atoms are still present and the contribution is 1 by 8. So A 7 by 8 B 3, that becomes A7 B 24. This is the formula of the crystalline solid. Now if you go ahead with again I'm just making a deviation from this particular first question. If two corner atom and 3 face centers are removed, what is the formula? So no problem, if two corner and 3 face centers are removed, the corner is having 6 by 8 and the face is having half, so 4 by 2 because 3 face centers are removed. If two corner atoms are removed and 3 face centers are removed, so here 3 face centers are removed, then it will become 3 by 2, okay. And if here if I said 2 face centers are removed, then this will be nothing but how many will be remaining? 4 will be remaining because 2 face centers are removed. So make it like this: 2 corner atom and 2 face centers are removed. 2 corner atoms are removed, 6 by 8. 2 face centers are removed, it is 4 by 2, it is 2, so it is A3 by 4, 2, so it becomes A3 B8 is the formula of the crystalline solid. And if 3 are removed, it will become 3 by 2 because each face center is having a contribution of half. Next we come on to. This is a fundamental question again. In a cubic crystal, atoms A are present at corners, atoms B are present at body center, and atoms C are present at face center. Determine the formula. That's very simple. ABC3. Why? A is at corner, B is at body center, C is at face center. You know the contribution of all and you can get the formula as ABC3. But deviations I am taking place from this particular question. If all the atoms along one of the body diagonals are removed, see, if all the atoms along one of the body diagonals are removed, what will be the formula of the crystalline solid? Just check it out, please. So what is we have done? If all the atoms along one of the body diagonals, so dear students, you can see the figure here. This is the body diagonal. If you remove one of the body diagonal, then this 2 corners will be removed and 1 body center will also be removed. So 2 corners are removed and 1 body centers are removed. So this is corners are removed means 6 by 8. Body centers are removed means 0 because there is no atom at the body, and face center will remain as such, no problem about it. 6 by 2 is equal to 3. Okay, so this becomes A6 C24 as a formula of the crystalline solid. Again, more questions we'll do right from here. Again, with respect to this particular questions only, deviations we are talking about. If all the atoms along one of the phase diagonals are removed, then what will be the formula? See, if you remove all the atoms along one of the phase diagonals, then this is the phase diagonal. And if you remove all the atoms along one of the phase diagonal, then this 2 corner atom and this face center atom will also be removed. And therefore, 2 corner and 1 face centers are removed. So this will be A6 by 8. B will remain as 1 only because you are not removing from the body. C will become 5 by 2. So this will be nothing but the formula will develop as A3, B4 and C10. So these are very important questions, which are asked in the examinations. Next one more. If all the atoms along one of the axes is removed, if body center is at origin, if all the atoms along one of the axes is removed, if body center is at origin. So if body center is at origin, so you can take this as axis, you can take this as axis. So what will happen? Two face centers will be removed and one body center will be removed. So one body center is removed means 0 is the body, corner will remain entirely as 1, and if you see two face centers are removed, so still 4 are left. So 4 by 2 will be 2 and formula will be AC2. So this is the formula of the crystalline solid. Next is, if all the atoms along one of the axes is removed, if origin is at any of the corner. If origin is at any of the corner, then let's suppose this is the origin, this is one corner and this is another corner. So two corners are removed, and if two corners are removed, so what will happen? Okay, only 6 are left up. So A 6 by 8, B will remain as such and C will remain as such because nothing has been removed from the body, nothing has been removed from the face center. So it is A 6 by 8, B1, C3. So it will be A3, B4, C10 as a formula of the crystalline solid. So this is what we have talked about, the deviations of the questions. 4 questions we have dealt with. We'll now move on to the next particular concept, that is calculation of density. When we talk about the calculation of the density, what is useful? The formula is very important, dear students, for calculation of density. Just remember the formula. Density is equal to Zm by Nv. What is Z? Unit cell content. M is molar mass. N is Avogadro's number. And V is the volume of the cube. So let's suppose one question is over here. A metal crystallizes in 2 cubic phases. Okay. FCC and BCC, whose unit cell length are 3.5 and 3 angstrom respectively. Calculate the ratio of densities, that is FCC upon BCC. Okay. So now the formula is what? Density is Zm by Nv. What is density of FCC? Unit cell content is 4. So 4 into molar mass upon N, and edge length you know that, A cube. So 3.5 to the power 3. Density of BCC is same thing, Zm by N, 3 to the power 3. So this Z is taken to be as nothing but 2. I am taking it as 2. Now nothing but this is density of FCC, this is density of BCC. Take it on the ratio side. So this is on the ratio side and you will get nearly 1.259 as the answer of the question. I hope everybody is clear. Next is this particular question I am dealing with. The edge length of the unit cell of a metal having molecular weight 75 gram per mole is 5 angstrom, which crystallizes in a cubic lattice. If the density is 2 gram per centimeter cube, calculate the radius of the metal atom. Need to consider Avogadro number as 6 into 10 to the power 23. Very simple. Density is Zm by Nv, dear students. So what is the density given to you? 2 gram per centimeter cube. Unit is also very important to be consideration. It is given in the CGS unit. So 2 gram per centimeter cube, which is equal to Zm. M is 75. Nv. So volume of the cube is A cube. So it is given 5 angstrom, which can be written as 5 into 10 to the power minus 8 and to 6 into 10 to the power 23. So if you do the calculation here, Z will come as 2, Z will come as 2. So we understood the arrangement is nothing but BCC. So once the arrangement is known to us, dear students, we can find out the radius, because what is the radius formula? Root 3a by 4. A is known to you, 4. Root 3a by 4, we can do it and we get the answer as 2.165 angstrom. So this is the answer to the question. I hope everybody has got this particular point, that 2.165. After calculation you will get the answer for this. Next we come on to the close packing. If you talk about the close packing, what is close packing? In close packing means arrangement of the atoms or the spheres, efficiently. That is called close packing. So here we talk about coordination number, and that coordination number is nothing but number of nearest neighbors. How many neighbors are there nearest to me? That is called coordination number. So if you talk about in one dimension, nothing but what? Coordination number is equal to 2. That is a linear packing we say. In 2 dimension, we have 2 types of packing. One is called as a SCP, square close packing, and hexagonal close packing. If you see square close packing, the coordination number is equal to 4. And if you talk about hexagonal close packing, the coordination number is equal to 6. So this is in 2 dimensions. See, already this is what I have told you, a visualization based chapter. So you need to see the structures, you need to see the colored full diagrams in order to understand it more efficiently. Okay. In 3 dimensions, we have 2 types of arrangement. One is called as hexagonal close packing and one is called as a cubic close packing are observed. And we have 2 types of voids over here. One is called as a TV type, one is called as a OV type of void. Tetrahedral void and octahedral void. In tetrahedral void, in HCP arrangement, if you talk about hexagonal close packing, the arrangement which we get is nothing but A, B, A, B, A, B, A, B. A, B, A, B, A, B, A, B type of arrangement we are getting. So what I mean is the third layer is repeating the first layer. So third layer is repeating the first layer. Okay. So this is called AB, AB, AB type of arrangement. Okay. So if you talk about the Z effective means effective number of atoms present in the hexagonal close packing, that comes out to be nothing but 6. And this is also very important. They will ask you in case of HCP, what is the unit cell content? That is nothing but 6. So 12 corner atoms, that is 1 by 6. 1/6 is the contribution in the corner atom over here because they are present in the hexagon arrangement. I'll show you. That is 2. 2 is present in the face, half contribution, that is 1. And 2 is present in the body center. 3 is present in the body center. So total is 3. So if you calculate this, this comes out to be 6 as nothing but unit cell content. Now if you go on to, I'm just showing you the arrangement over here. If you can look into. This is a hexagon over here. This hexagon, if you see, this is the top of the hexagon, this is the base of the hexagon, and if you see any corner atom of the hexagon, these are all corner atom of the hexagon. All these corner atom of the hexagon is a 3-dimensional mix and contribution of 1 by 6. So total how many corners we have, dear students? It is nothing but 6 on the top side, 6 on the bottom side. So basically it is 12. So 12 into 1 by 6 will make it as 2. And center, this is a center atom, that is a face center I'm talking about, half. And this 3, if you see this one, if you see this one, and this one, they are present in the body of that particular hexagon. So they are not sharing with anything else. So their entire contribution is taken to be nothing but 3. So we have 2 from the effective number of atoms from the corner is 2. Secondly, 1 from the effective number from the face, and 3 totality has been taken as from the body, and total, that is Z effective. This is what comes out to be 6. This is what I'm talking to you. So this is what you need to remember, dear students, among the type of contribution which we are talking about. In CCP, if you talk about, the 4th layer repeats the 1st layer. In hexagonal close packing, the 3rd layer repeats the 1st layer. Okay, in CCP, the 4th layer repeats the 1st layer. So this is nothing but ABC, ABC, ABC. 4th repeats the 1st. And if you talk about the effective Z efficiency, that comes out to be 4. So this is nothing but CCP only. Okay, so in cubic close packing, CCP is also called as FCC also. So FCC also, where the Z effective comes out to be 4. So the difference, I hope you have understood. One point of I'll talk to about, as far as coordination number is concerned, in both HCP and CCP, it comes out to be 12. As far as mode of packing percentages are concerned, they are both 74%. Okay, they are same, but the difference is also there. What? In HCP, the third layer repeats the first. In CCP, the fourth layer repeats the first. In HCP, the unit cell content is 6, while in CCP, the unit cell content is 4. So this is what you remember, and you can solve up the questions related to this particular part. Next, we come on to the location of the tetrahedral and the octahedral void in a cube. So if you talk about the location of the tetrahedral void and the octahedral void in a cube, see, tetrahedral voids, if you talk about, they are located on the body diagonals. Tetrahedral voids are located on the body diagonal. In each body diagonal, we have 2 tetrahedral voids. So total we have 4 body diagonals. 4 into 2 is 8 tetrahedral voids are there. That is what I said. Each BD, each body diagonal, 2 TV. So 4 BD is 8 tetrahedral voids. And you can see this arrangement which I am showing to you. This is the arrangement of the lattice. Now if you check here, you can see that the arrangement over here, there are 4 body diagonals. This one you can see, this is 1 T. Wherever T is written, circled T, they are nothing but the tetrahedral void. This is 1 T, this is another T, this is another T. Actually this is overlapping, you can see, because it's a 3-dimensional, you can see like this. But if you go into actual, it is not like that. So there are 2 tetrahedral voids, 4 tetrahedral voids in this particular, because there are 2 body diagonals. So we have 8 tetrahedral voids, and they are located in the body diagonal in a cube, and each body diagonal has 2 tetrahedral voids. Again, if you want to see up, I'll show you the arrangement of a lattice. If you see this lattice, these are 8 small cubes I have made up, okay, and this is 8 tetrahedral voids per unit cell of CCP. There are 8 tetrahedral voids per unit cell of CCP. So if you see this corner, this one, and this one, these are making the tetrahedral arrangement, okay, and this is the void over here. So when you make a tetrahedral, 4 spheres are making a tetrahedral arrangement. So out of this 8, we have just taken out this particular arrangement, if you can see. So this is what I'm talking about. The atoms are present at the alternate corners. This one, if you talk about, then they are present at here, okay, then they are present at here and here. If you arrange all this, direct or attach all this, then there will be a tetrahedral arrangement, and it makes a void over here at the center somewhere like this. This will be a tetrahedral void. So what I'm trying to say you, it is one tetrahedral void showing the geometry. I'm showing you the one tetrahedral voids here. An FCC unit cell has been divided into small cubes. We have divided it into small cubes such that the center of each subcube is the location of the tetrahedral void. Such that the center of each subcube is the location of the tetrahedral void. So I hope you have understood what is the arrangement of the tetrahedral void. It is located in the body diagonals. Okay. Similarly, if you talk about the octahedral voids, I'll show you the octahedral voids also. So this is what I've shown you earlier, that T means the tetrahedral void which are present in the body diagonal. So this is what the body diagonal we have. You can see the arrangement. Specifically, you can see there are 4 body diagonals and 8 tetrahedral voids we have. Let's see the octahedral voids. How is the octahedral voids arrangement? So this is the octahedral voids arrangement. If you see, we have this particular lattice. Location of the octahedral void. So we have 12 octahedral void on the 12 edge center. So all this which you are talking about, this particular, this, all this, you are talking about edge center. On each edge center, there is one octahedral void, okay? And one full octahedral void, I am saying one full octahedral void is present at here point, this one. Got it? It is not sharing with anyone. But the octahedral void present at the edge center is having a contribution as 1 by what? 4. So 12 into 1 by 4 is equal to 3. I said contribution is 1 by 4. There are total 12 octahedral voids at the H center. So 12 into 1 by 4 is equal to 3. So effective number of octahedral voids at the H center is 3 only. And one full octahedral void is present at the center. So 3 plus 1 is nothing but 4. 4 is the total number of octahedral voids. So we can check, as I said, there are 8 tetrahedral voids. So there are 4 octahedral voids effectively. So what is the relation between the tetrahedral and the void and the octahedral void? There are 4 octahedral void. There are 8 tetrahedral void. So there will be one octahedral void, so there will be 2 tetrahedral void. So that is what I have told you right away. There are 12 H center, 12 octahedral void. 12 into 1 by 4 is 3 octahedral void effective, and 1 total at the body center. Total comes out to be 4. So what is the relation between TV and OV? We have 8 TV, we have 4 OV. So we have 2 TV, we have 1 OV. So for one OV we have 2 tetrahedral voids are present. Okay. So if you talk about now, as you have understood, there are 1 octahedral void. For that one we'll be having 2 tetrahedral void. Okay. So naturally the size of the octahedral void also should be nearly double of the tetrahedral void, and that is what we will come into the later discussion, that the size of the octahedral void, that is in the radius ratio, comes out to be 0.414. This is the size of the octahedral void, 0.414, that is a limiting value, while the size of the tetrahedral void is 0.225. So if you check 2.225 and 0.414, nearly double is the relationship between the tetrahedral and the octahedral voids. Now let's talk about the arrangement and the packing, because voids are there. Okay. In a cube we have 14 atoms. Total 14 atoms are there, as spheres are there. Got it? Where there are 14 atoms, 8 are present at the corners. These are the corner ones, which are present as 8. 8 are present at the corners, and 6 are present at the face centers. So this one, this one, this one, this one, this one, and this one are present at the face centers. So 6 face centers and 8 at the corners. So 8 corners effectively is gonna to be 1, and 6 face centers effectively is gonna to be 3. So 3 plus 1 gonna to be nothing but 4. So the total is nothing but 4 spheres we have, and for that 4 spheres are there. And how many atoms are there? If you see the atoms, let's suppose only the octahedral void, if you see, there are total 14 atoms, 8 at the corners and 6 at the face center. 14 atoms. Effectively it is coming as 4. And how many octahedral voids are there? 12 at the H center, 1 at the body center. 12 plus 1 is 13. Okay. So effectively octahedral void is 4. So 4 spheres, there are 4 octahedral void. 4 spheres, there are 4 octahedral void. So one sphere will have 1 octahedral void and 2 tetrahedral void. So that is what I am saying you here. Number of spheres is equal to number of octahedral void. So number of tetrahedral void will be double. Okay. So if there are n spheres, there are n OV, and if there are n OV, there are 2n as the TV over here. This is what the point of discussion is. I hope you have understood. One more thing I like to show you here entirely. Just check it out. As we have said, let's suppose this is a cube, and from here A to this particular B, the entire length of this AB is 1. AB is a body diagonal. It is taken as 1. So where is the tetrahedral void present? It is present on the top 1/4 AB. 1/4 of AB. This is entirely AB. So I'm saying this 1/4 is the tetrahedral void on the top. 1/4 is a tetrahedral void again present in the down. and this entirely from this point to this point, which is half AB, is a location of the octahedral void. That is what also we come into the conclusion that if there is half occupying space of octahedral void, this 1/4 only occupying tetrahedral void. The size of octahedral void is double the number of tetrahedral void. So if at all you are going to remove this particular body diagonal, then how many atoms will be removed? You know, 2 of corners will be removed. This is the corner atom. 2 of these corners will be removed. 2 tetrahedral voids will be removed, and 1 octahedral void will be removed, which is at the center of the cube. So 1 octahedral void, 2 tetrahedral void, and 2 corner atoms will be removed if you remove this body diagonal. So question will be there, you know, just check it out what I told you right now. Now let's come on to the next discussion, which is nothing but related to the questions of voids. This is a tetrahedral and octahedral void. What the question says that in a cubic crystalline solid, the lattice is made up of oxide ions. Okay, 1/8 of tetrahedral voids are occupied by A2 plus. This is A2 plus, and half of OVs are occupied by B3 plus. Okay, 1/8 of TVs are occupied by A2 plus, half of OVs are occupied by B3 plus. What will be the formula? Very simple it is. See, as I told you, if number of spheres is n, number of octahedral void is also n, and number of tetrahedral void is 2n. So we are just taking who is making the lattice? Oxide. So if there is oxide, one oxide, if one O2 minus is there, which is making a lattice, simple, ekdam simple representation we are going. If there is one oxide, then corresponding to that we have one OV, and for that one OV we have 2 TV. This is what the point of discussion. You can take the big number also. If there are 100 oxide, there are 100 OV and there are 200 2V. But why to take? We go on to the minimum numbers. Now, A2 plus, 1/8 of TVs are occupied by A2 plus. 1/8. How many TVs are there? 2. 2 TVs are there. So 1/8 of TVs, that is 1/8 into 2 will be 1/4, that is A2 plus. So A2 plus is nothing but it is just coming as 1/4. Okay. Now, half of OVs are occupied by B3 plus. Means what is B3 plus? Going into octahedral void? No. And how many octahedral void are there? 1. So half of 1 is half only. Okay. So O2 minus is 1. A2 plus is 1/4. B3 plus is 1/2. Now convert into the integral number by multiplying with the suitable number. You will nothing but you will get AB2O4. AB2O4 is the arrangement of this particular here. Next we come on to one more question dealing with this. In a compound, we are just coming into the reverse of the particular question which you have just discussed, reversed. Earlier what we did is we determined the formula. Now we are determining the percentage of the occupancy of the tetrahedral and the octahedral void. We know the formula, we are determining the percentage occupancy. So in a compound AB2O4, oxide ions are arranged in CCP. What percentage of TV is occupied by A2 plus, and what percentage of OV is occupied by B3 plus? Okay, I hope you have understood the question. It's over here only. Okay, so who is making the lattice? Obviously oxide. So if there are 4 oxide, there are 4 octahedral void, and if there are 4 octahedral void, there are 8 tetrahedral void. Okay, so who is going into the tetrahedral void? It is said what percentage of TV is occupied. So basically A2 plus, A is going into tetrahedral void. How many tetrahedral void we have? 8. How many atoms of A are there? Only 1. So obviously out of 8 tetrahedral void, only 1 will be occupied by A, and therefore the percentage occupancy will be 1/8 into 100, which is 12.5%. Similarly, how many OVs are there? 4. But how many B atoms are there? 2. So it is nothing but 2/4 into 100, that is 50%. So this is nothing but called as what? The solving of the question. I hope you have understood it. Let's go on to more other than this questions. We'll do 2 more questions. We'll do try to understand that. so that the concept goes into your brain mindset. The compound is formed by A, B, C. A is arranged in CCP, okay. B is present in 25% of TV. C is present in all the remaining voids. I hope you recall this question. B is present in 25% of TV. C is present in all the remaining voids. Remaining means TV as well as OV. Determine the formula. Okay. A is equal to 1 because lattice is formed by A. OV will be 1. TV will be 2. Now what is saying? B is present in 25% of the TV. Okay. What is 25% of 2? That is half. So this is B. How many tetrahedral voids were there? 2. Out of that only half is occupied. So 3 by 2 is remaining. Unoccupied. 3 by 2 is unoccupied. Okay. Who will go there? C. Because C is present in all the remaining voids, TV as well as OV. Okay. Now C will occupy. How many OV? 1. How many TV? 3 by 2. So 1 plus 3 by 2 is what? Check. 5 by 2. So A will be 1. B will be half. And C will be 5 by 2. And you can convert this into the integral numbers. Convert into integral numbers and you can get the answer of the questions. I hope you have understood it. One more question will do. A compound is formed by ABC. Atoms C are present in FCC. B is present in 1/3 of OV. B is present in 1/3 of OV. And atoms A is present in 75% of remaining of OV and 25% of TV. Question is in front of the screen only. Okay. Who is making the lattice? C. If C is 1, OV has to be 1. TV has to be 2. B is present in 1/3 of OV. How many OVs are there? 1. 1/3 of 1 is nothing but 1/3 only. So 1/3 is occupied. How many is unoccupied? 2 by 3rd. Because 1/3 is occupied. 2 by 3 is remaining. Okay. Now A is present in 75% of remaining of OV and 25% of TV. Got it? So A will be what? 2 by 3 into 75%. 2 by 3 into 75% plus 2 into 25 by 100. Why? Because how many tetrahedral voids were there? 2. So out of that 25% of 2 is half and 75% of 2 by 3 is 0.5. So if you add up both it will come as 1. So C is 1, B is 1 by 3, A is 1. Convert this into the integers, you will get the answer of the question. So I hope we have discussed nearly 4 questions related to the voids of tetrahedral and the octahedral. Your confusions and your concepts will be more cleared now. Let's go on to the next part of discussion. We have radius ratio now as a part of the discussion. What is radius ratio? Radius ratio is very simple. That is the radius of cation by radius of anion. Who makes cation is nothing, it is the radius of the void. Anion is nothing, the radius of the sphere. So anion makes the sphere and cation makes the void. Okay. So we have so many voids are formed up with the spheres. If we have 3 spheres, that will be called as triangular void. If we have 4 spheres making a packing, then the void is tetrahedral. If we have 6 spheres, then it is called octahedral. If we have 8 spheres, it is called cubic. So 3 spheres, if you calculate what is the limiting value of the void, what is the fitting value of the void, then it will come 0.155. Okay. So if coordination number is 3, 0.155. And the range of, see, this is the fitting value, means below this the void is not possible. Okay. If you talk about coordination number 4, then it will be 0.225. And if you talk about 6, 0.414. If you talk about 8, 0.732. All these are limiting value. So this 4-1 is nothing but tetrahedral void. 6 is nothing but octahedral void. And rest you know that it is triangular and the cubic void. So what is a fitting value? All these are called as fitting value. And the range of these voids are nothing but the value of the next particular void. So this range is 0.155 to 0.225. This is 0.225 to 0.414, and this is 0.414 to 0.732, and this is 0.732 to 0.93. So this is the fitting value or the void value. We'll just calculate one so that you can understand, okay, the mathematical part of it. This is nothing but the four spheres are there, and this is the cation which is fitted into here. See, four spheres only will be able to show because it is a three-dimensional. So one will be coming from the top, one will be coming from the downside. So we can show here 4. So this is nothing but anion, 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 anion. This is cation. So this is R, and this is 2R. So if this is hypotenuse, this is height, and this is base. So hypotenuse square is equal to height square plus base square. So hypotenuse is what? 2RA plus 2RC. Height is 2RA, base is 2RA. So this is 2RA plus 2RC, 2RA, 2RA. Then calculate what? Just after this opening the square term, then calculate RC by RA. Okay. And if RC by RA is 4.414, this is the limiting value of the octahedral void. If RC by RA is less than 0.414, when it will become less than 0.414, you know, when the size of the cation will be lesser than this value, then the void will become disturbed. So it won't be octahedral, it will be a tetrahedral void. And when RC by RA will be greater than 0.414, means the size of cation will be little bigger than this particular fitting value. Okay, fitting means fitting. Here the fitted value is there because, say, this is why this is called fitting value, limiting value, because all anions are touching each other. Cations is also touching the anion. But if the cation becomes smaller, it will not touch. If the cation becomes bigger, anions will not touch each other. So this is what I'm talking about. So if RC by RA is greater than 0.414, then it will become till 0.732, it remains octahedral void. You can talk the mathematics of it. That's what I have shown you here. This is all four spheres are there, and these are all anions, and these are cations. So you make a triangle here. This is A, B, C, and D. So in triangle, if you talk about the angle BAD, if you talk about this particular angle, then this particular angle BAD is 45 degree, and cos BAD is cos 45. In triangle ABD, isn't it? AD, this is AD, and this is what? AB. So AD by AB is equal to cos 45. And if you talk about AD, what is AD? RA. And what is AB? RA plus RC, which is equal to 0.7071. So if you go on to the calculation of this, it will come out 0.414 is a value of radius ratio. This is how we get it. So likely we can calculate for others. We don't have time right over here for the calculation of all. That's the mathematical ones. You need to remember this, or you can do it the mathematical way I have done this. Next we come on to the structures of ionic compounds. If you talk about the structures of ionic compounds, basically we have AB type of compound. We have AB2, we have A2B. AB, we have many ones. We have NaCl is there, cesium chloride is there, zinc sulfide is there. They're all a part of AB type of arrangements. And next is AB2 is calcium fluoride. Next is A2B, we have nothing but sodium oxide. So we have these types of arrangement over here. So if you talk about the, for knowing what will be the radius ratio, we should know the ionic radius of sodium and chloride, cesium and chloride, zinc and sulfide. We should know. Okay, and that is not possible for us to cram those values. So just remember what? RC by RA, I'm just talking about the first discussion is sodium chloride. RC by RA comes out to be nothing but 0.414 to 0.732 in case of sodium chloride. So this will fall under what? Octahedral void. So octahedral void, who will make the lattice? The bigger ones will make the lattice. That is, this is 0.41. This actual value is 0.526 by 1. So means the size of sodium ion is 0.526 and the size of anion is 1. Okay. So who makes the lattice? The bigger one. Chloride ion makes FCC lattice, and Na plus occupies octahedral void. Okay. So where will be the octahedral void? 12 sodium ions are present at 12 H centers. Effectively, you know it is 3. 1 at the body center, you know it is 1. So total is called as 4. So basically we have 4 what? Na plus. And how many chloride ions are there? They are making the arrangements. They are present at 8 chloride are corners and 6 chloride faces. Effectively will be 4. So what is the formula? There are 4 sodium and 4 chlorine, and therefore we get Na4Cl4 arrangement as NaCl. And if you see the important thing also, one thing is we got the arrangement, and if you see the coordination number, I'll show you here. Just see the colored full diagrams. If you see here the colorful diagrams, if you talk about the edge length, see the bigger ones are chloride. So these all green ones are chloride, and the red ones are nothing but sodium ions. If you see the green ones from this distance to this particular distance, if you check, okay, this is chloride to chloride. Okay, from this part to this particular part, this is our radius of cation, radius of anion, and this is radius of cation, radius of anion. So basically what we can say, edge length is nothing but equal to what? 2 times of what? Rc plus Ra. So edge length is nothing but A is equal to 2 times of R plus R minus. This is what I have shown you also with the discussions. And what is the coordination number? If you see the red one over here, just see only the red ones, okay? Because for green one, we need to make another arrangement now, because it is a continuous arrangement. If you see this red one, okay, which is sodium ion, isn't it? This sodium ion is surrounded by this chloride, this chloride, this chloride, this chloride. So this is totality 1, 2, 3, 4, 5 and 6. So coordination number will be what? 6. So each sodium ion is surrounded by 6 chloride, and each chloride will be surrounded by 6 sodium ion. This is called as a coordination number in case of sodium chloride. This is what the structure. Please feed this part in your brain, so that examination you will not be able to make this diagrammatic representation. You need to remember this, what the edge length is equal to 2 times of R plus R minus. Okay. Next we come on to the arrangement which I am showing you, nothing but of cesium chloride. I am showing you what is cesium chloride. Again you need to find out the radius ratio, and you find it out. Chloride ion makes the BCC lattice and cesium ion occupies a void, because radius ratio here comes out to be 0.92. Okay, so chloride ion makes the BCC lattice, I am saying, and cesium ion occupies a void formed by 8 spheres. Okay, so formula is nothing but cesium chloride, and coordination number will be nothing but 8:8. 8:8 is the coordination number ratio. Now if I show you, please try to understand this particular arrangement. What? This is what all the green ones which have been shown you, okay, they are nothing but cesium ions. So if you just concentrate on only one particular arrangement here, so this is cesium ion, this is the green one on the next next cube, behind the cube which I am talking about. So if you just see this one, this particular cube, these all these corner ones, these are nothing but what? Chloride. And this is nothing but what? The center one is nothing but cesium. So this is cesium and this is chloride. And if you see the bigger version of it, that is what I was showing you here. Now see here, each cesium is surrounded by 8 chloride, and each chloride is surrounded by 8 cesium. So if you come on to the coordination number, 8:8 is the coordination ratio, while in case of NaCl it was 6:6. I hope everybody has understood with this particular arrangement. Next we come on to zinc sulfide. If you talk about zinc sulfide arrangement, again you will find out the radius ratio, and that radius ratio comes out to be what? Radius of zinc ion by radius of sulfide ion. That comes out to be value as 0.40. Okay, so 0.40 is the value of zinc ion. So zinc ion will make what? This falls under what? Tetrahedral void, because tetrahedral void is 0.225 to 0.414. Okay, so sulfide ion makes the FCC lattice, and zinc ion occupies the tetrahedral void. And as you know, each tetrahedral void is formed by 4 spheres. So each zinc ion will be surrounded by one zinc ion surrounded by 4 sulfide, dear students. Okay, and the reverse, one sulfide will also be surrounded by 4 zinc ion. Why? Because the formula is what? ZnS, 1:1. So coordination number will be what? Simple. It will be in the same ratio as earlier, 6:6, 8:8. Now here it is coming as 4:4. But dear students, how many tetrahedral voids are there total? 8. But how many zinc ions are there total? 4. What it means? That total there are 8 tetrahedral void, but only 4 are occupied and by zinc ion alternatively. So 50% is occupied and 50% is what? Unoccupied. That is what it will ask in the examination. So this is how the arrangement of, if you can see, this is nothing but ZnS. See, sulfide ion makes the red ones and the green ones are the zinc ions. So if you see carefully, okay, then you will acknowledge that each zinc ion is surrounded by 4 sulfide. This zinc is surrounded by this one also, this one also, this one also, and this one also. So one is surrounded by this, one is surrounded by this, one is surrounded by this. Okay, like this arrangements we are talking about. So this is the structure of zinc sulfide. I hope everybody has understood with this pictorial representation. Next we come on to calcium fluoride. In calcium fluoride, who makes the lattice? Here is the reverse case actually. In calcium fluoride, the size of calcium ion is greater than the fluoride ion. Cation is bigger than the anion. So instead of doing Rc by Ra, what we'll do is Ra by Rc. And that value again comes out to be 0.225 to 0.414. So tetrahedral void only. So who will go into the void, dear students? Fluoride ion will go into the tetrahedral void. And who will go into the, who will make the lattice? Calcium ion will make the lattice. Okay. Calcium ion will make the lattice and fluoride ion will go into the tetrahedral void. So one fluoride, see, for making the tetrahedral void, you need to have 4 spheres. So who is going into the tetrahedral void? Fluoride. So one fluoride will be surrounded by 4 calcium ions. So 4 2s are 8, that is 8 positive charge. One calcium is surrounded by 8 fluoride, so that is 8 negative charge. So what is the coordination number ratio for calcium fluoride? Each calcium surrounded by 8 fluoride. So 8 is the coordination number of calcium, 4 is the coordination number of fluoride. So coordination number ratio is 8:4, and if coordination number ratio is 8:4, then it is 2:1. Then the formula ratio is just reverse of the coordination ratio, that is 1:2. And this is what the structure of calcium fluoride. Dear students, please check and acknowledge this is what the structure of calcium fluoride. You can see that fluoride ions, okay, are going into the tetrahedral void. So these green ones are the fluoride ions, and the blue ones which has been shown, they are the calcium ion which are making the lattice. And you see all the tetrahedral voids, there are 8 green ones. So all the tetrahedral voids are occupied here. So I hope you have understood it all. Everyone? Okay. This is what. Next one thing more remaining, that is called as Na2O, sodium oxide. So if you talk about sodium oxide, is normal actually, not a problem. Sodium oxide. What is there in sodium oxide? It is an isoelectronic species, so radius of sodium ion will be less than the radius of oxide ion. If you go on the calculation of radius ratio, it comes out to be 0.225 to 0.414. So sodium plus makes the tetrahedral void and oxide makes the lattice. So when sodium plus makes the tetrahedral void, so one sodium is surrounded by 4 oxide. One sodium surrounded by 4 oxide. Okay, 4 2s are 8 negative. And one oxide is surrounded by 8 sodium. So 8 positive. So it is nothing but 4:8. If you see, one sodium surrounded by 4 oxide. So coordination number of sodium is 4. Coordination number of oxygen is 8. So 4:8, that is nothing but 2:1. So this is what the formula we have got it as 2:1. So we have discussed all the particular types of uh, voids all the particular types of arrangements over here and the radius ratio correspondingly. Okay, next we come on to defects in solids. Have you ever thought about why there are defects in the solids? The defects in solids are because of the important thing I come up the discussion, that is called entropy. What is entropy? Measurement of disorderness. So if you say at absolute zero, the crystals are having what? Perfectly ordered arrangement. Okay, and that corresponds to the state of lowest energy. Okay, so when temperature increases, what happens? The crystal will start deviating from the perfectly ordered arrangement. So any deviation from this perfectly ordered arrangement will constitute an imperfection or defect, and therefore these are also called as thermodynamic defects. So thermodynamic defects because when temperature increases, crystal starts deviating from perfectly ordered arrangement. So when temperature is equal to 0 Kelvin, S is equal to 0, this is the absolute value of entropy, no defect, and that is called perfectly crystalline solid. Perfectly crystalline solid. We have other types of defect along with this. We have stoichiometric defects. In that we have a Schottky defect, and in this Schottky defect, what happens? Equal number of ions are missing from the lattice side. That is, one cation and one anion are missing from the lattice side. And second thing is, it is mostly common in the ionic compounds and is seen with the high coordination number where the size of cation and anion are almost equal. Example you can remember: KCl, KBr, CSCl, NaCl. These are all examples of Schottky defect. Okay, and these large number of Schottky defects, results in significant decrease in the densities. Okay, presence of large number of Schottky defect in crystal results in significant decrease. Otherwise, normally the density, we say that in comparison to the other, the density remain unchanged. Let's come on to the next one, that is called as a Frankel defect. The cation is missing from the original lattice site, okay, and occupies interstitial site. Low coordination number and difference in size of cation and anion are also high. So this is what we have discussed about the Schottky defect, the Frankel defect, and the solid state. This is the entirely a part of discussion for this. Next we come on to the periodic classification of elements. If you talk about the periodic classification of elements, we come on to valency. What is valency over here? Nothing but the combining capacity of element is called as valency. Okay, and we also call as number of unpaired electrons in the ground state or excited state is also called as valency. So alkali metals, the valency is 1, alkaline earth 2, boron is 3, carbon is 4, nitrogen is 3 and 4, phosphorus is 3 and 5, oxygen is 2, sulfur is 2, 4 and 6, common discussion is there, fluorine is 1, chlorine because of the variable, sulfur is also because of the variable, valency is 1, 3, 5, 7, and xenon also exhibits 2, 4, 6, 8. So earlier xenon was called as a noble gas family, but now it is no longer called as a noble gas family because xenon is the element which has a tendency to form compounds with highly electronegative elements like fluorine and oxygen. Okay. Now, if we talk about the calculation of period, groups, and all discussions. So, right now we are just focusing on the calculation of nothing but calculation of periods, group, electronic configuration that you can do because you know the atomic structure part, atomic structure configuration, period, group, and block, like that. So if we have been given an arrangement, for example, if it's an S block element and the configuration is given 5S1, so the first number is 5 and that represents the period number. This represents a group number which is equal to 1, and this is nothing but it is called as S block. So any S block element, the first number which is written is a period number, and the top number is written as a group number. Same is with the, if I talk about nothing but if I say it is 4p3 for a P block element, okay. So number is written 4, so this is also gonna to be period number, and this is nothing but you know that P block it is, and top is written 3, so you can add 12 here. Why? Because the P block starts from group number 13. So 3 plus 12 is equal to 15th group it is. So whenever it is a P block element, you need to add 12 in the group so that you get the actual group number. If it is nothing but, let's suppose arrangement is 4D1. So it's a D block element, no doubt in it. It's a D block element. The number first is written as 4. You need to add plus 1. So you will get 5th period. And in the top, it is written as 1 here. You need to add 2 here to get the group number, which is equal to 3 for the given configuration. So whenever for D block element, you need to add 2 in the group, and for in the first number you need to add 1. And if you talk about F block element, which is nothing but 4F7, let's suppose, then the number 4 represents nothing but not the period number. You need to add plus 2 to get the 6th period, and this is nothing F block. Okay, this 7 number is not the group number, dear students, because all F block 28 elements, they go into the common group as third group. So this is how you have understood how to calculate the period, block, group, and the configurations. Already you know how to do that. Let's go on to the next discussion about screening effect. So what is screening effect, dear students? Actually, the valence electron in a multi-electronic atom, the valence electron in a multi-electronic atom is attracted by the nucleus and is repelled by the electrons present in the inner shells. The combined effect of this attractive and the repulsive force acting on the valence electron is that the valence electron experiences less attraction from the nucleus, and that is nothing but called as a screening effect. So if you see, this is the nucleus over here, and this is the outermost electron here. So between this nucleus and electron, there is a force of attraction. Got it? So between this force of attraction, there are other electrons also which are present in the inner shells, which are repelling these electrons. So what will happen? Whatever be the attraction, the value of that attraction will decrease because of the number of electrons present in the inner shells are more, and that those electrons are repelling this particular test electron. So actual amount of charge, actual Z, this is Z, which is called as a nuclear charge, which you expect is nuclear charge, and which is actual, it's just called effective nuclear charge. So effective nuclear charge is also called as a reduced nuclear charge, and that reduced nuclear charge is nothing but it is due to screening effect. So that is only the screening effect which I have told you right now. So the formulation, as I have shown you here, the electron, which is a test electron, which is getting repelled, is present in N, and the electrons which are repelling, they are present in N-1, N-2, N-3. Electrons can also be present in nth also. Very important formulation, Z cross is equal to Z minus sigma. So what is sigma? This is the screening constant per electron. Z actually I told you, okay, which you expect as Z, and which is actual is effective nuclear charge. So for hydrogen, Z cross is equal to Z, because in hydrogen there is no electron, there is only one electron which is there, no other electrons are there for the repulsion. But for helium, the value of sigma, that is helium, there are two electron system, no? So there are two electrons, this is helium, this is nucleus, so there are two electrons. So this one electron, if you take it as a test electron, okay, then this test electron is repelled by this electron, and with the value 0.30, and these are present only in nth only. So the value of sigma is 0.30. So Z cross, you can find it out. That is nothing but Z minus sigma, 2 minus 0.30, 1.7. So this is 1.7, the effective nuclear charge. So percentage attraction will be nothing but what? 1.7 upon 2 into 100, which is nothing but equal to 85%. So this is 85%, which is the percentage attraction. Earlier we were expecting 100, but actually it is 85%. So what we come to the conclusion, so as the value of Z cross goes on increasing, the force of attraction will increase, the atomic size will decrease, and ionization energy will increase. More the effective nuclear charge, more the attraction, smaller the size, more the ionization energy, more the electron affinity, and more the electronegativity. These all will be enhanced. And which will provide the maximum screening, dear students? Which s orbital or d? Then s is present near to the nucleus, more attraction, so entire power of that attraction will be utilized in repelling the test electron. So the maximum screening will be provided by s, then p, then d, and then f. So many questions comes in inorganic, gallium, aluminum and gallium, abnormal size, ionization energy. The answer comes with the screening effect only. Next we come on to the calculation values. If you can remember this table, that will be very convenient. These are nothing but sigma. This is sigma per electron. Per electron. The repulsion, the electrons who are repelling per electron, what is the value? If they are present in S and P, nth shell 0.35, n minus 1 0.85, n minus 2 1. If they are present in DNF, same nth 0.35, 1 and 1. Let's come to the calculation. I'm showing you one calculation of nitrogen. The configuration is 7, which is 2 and 5. So this is the nucleus, this is 2 and this is 5. So out of 5 students, you can take one electron, this one blackened one, as the test electron, and all these red ones which I am doing, they are nothing but the electrons which are repelling these particular electron. So how many electrons are present in the same shell? That is N, 4. 4, 1. These 1, 2, 3, 4, they are all 4 are repelling this particular electron. So 4 into 0.35 will be 1.40. So these two are present in N minus 1 and their values are present as 1.85. So 1.7. So 1.7 plus 1.4 is 3.1. So nitrogen atomic number is 7 minus 3.1 is 4.90. So this is the value of Z cross, and you can find out the percentage attraction also. I hope you have understood it. Please understand very cautiously. I have explained you with the table here. The value is also given in the table. With respect to that, I have explained you. One more problem I will explain you. Just check that. Fluorine, that is 2,7. So this is nothing but 2 and this is nothing but 7. So all the red color which I am doing is the electrons which are repelling that black electron. So how many are here? 6 into 0.35, that is 2.1, and here is 2 into 0.85 is 1.7. Totality comes out to be 3.9. 9 minus 3.9, that is nothing but Z cross. Along group. So along group, if I talk about, I'm just talking about how is the variation in the group. Sodium 11, 2, 8, 1. Outermost shell is 1, n minus 1, n minus 2. Okay, so this is the one electron which is getting repelled. There is a difference in getting repelled and doing the repulsion. This is the electron which is getting repelled. Nobody is there to repel the electron. So they are present in n minus 1. There are 8 electrons present in n minus 1, 0.85. 2 electrons present in n minus 2. Each value is 1, already told. So if you do the calculation, this will be 6.8 and 2, 8.8. And atomic number is 11. 11 minus 8.8 comes out to be 2.2. So 2.2 is a value of what? Z cross for sodium. Why I am showing you sodium here? Because I want to tell you that when you go down the group, the Z cross remains constant, leaving the top member of the family. So if you talk about potassium now, the value of the potassium comes out to be 2, 8, 8, 1. So this is nothing but nth, n minus 1, n minus 2, n minus 3. So in the nth there is 1 electron. So how many are repelling? 8 are repelling in n minus 1. So its value is 6.8. n minus 2, n minus 3 are taken as 1 only. So it is 10. So 10 plus 6.8 is 16.8. So if you check the value of 16.8, this is a big value, sigma, 16.8. Earlier the sigma came as 8.8. Here it is coming as 16.8. See how much it dominated going down the group. So 19 minus 16.8 come at 2.2. So for sodium it was 2.2. For potassium it is 2.2. So while going down the group, the value remains as 2.2. So what is the conclusion we came on to is along the period when you go, Z cross dominates more than the sigma. When Z cross dominates more than the sigma, then what will happen? Z cross dominates more than the sigma, then what will happen? Z cross increases, force of attraction increases, atomic size decreases, ionization energy increases, electron affinity increases, electronegativity increases. This is all the effect which is there across the period in the periodic table. So when you go down the group, along the group, I have shown you also with sodium and potassium, the value of Z cross is 2.2, that remains constant. So going down the group, along the group, sigma increases, atomic size increases, force of attraction decreases, ionization energy decreases, electron affinity decreases, electronegativity also decreases. So this is what very, very important thing you need to remember, the discussion which we have done right at the moment. Please remember, students. Next we come on to ionization energy. What is ionization energy? You already know aware about the ionization energy. Energy required to remove the electron. So when I'm saying it is energy required to remove the electron, obviously it is an endothermic process. Okay, it is an endothermic process. Half-filled and fully filled orbitals are more stable. Half-filled and fully filled orbitals are more stable as compared to which is not half-filled and fully filled. Okay, so if n is same, 3s, 3p, 3d, s is greater than p greater than d. If n is different, 4s and 3d, so what will happen? When n is same, 3s, 3p, 3d, then the energy required to remove the s electron will be very, very high. But if n is different, 4s and 3d, then what will happen? 4s will be far away from 3d. So easily the electron can be removed from where? The 4s, because that is the outermost. Okay, and 3d is penultimate. Okay, let's come on to the evaluation of ionization energy. If we have carbon, nitrogen, oxygen and fluorine. See, only one parameter doesn't decide the ionization energy. Half filled, fully filled, there are many other parameters. So if you talk about carbon, nitrogen, oxygen and fluorine, carbon is 2p2, nitrogen is 2p3, oxygen is 2p4, fluorine is 2p5. Now, where is the stability? Stability is nothing but 2p3. Okay, so whatever is left to and right to stability, stability will always dominate with respect to the left and the right. Okay, so with comparison to carbon and oxygen, nitrogen should have more ionization energy. But when you compare between nitrogen and fluorine, they are not next to each other, they are just next to next. So whenever it is a comparison of next to next, so the size factor comes into action. So with nitrogen and fluorine, okay, nitrogen is half filled, so that half filled stability you cannot proceed till fluorine. Why? Because size of fluorine also gets decreases. Okay, and so more energy will be required. So if you compare between nitrogen and fluorine, fluorine will have more. So what did I said? Once more I am saying, if there is a stability left and right to the stability, then stability will be dominating, means more energy. But if there is a stability and you compare next to next, means this and this, then the size factor will dominate and fluorine will have more ionization energy. Okay, and if there are two stabilities and those two stabilities are like this, stability to the next, to the next, to the next is stability. So in between there are two, then again size factor will dominate, which I am showing you in the problems. So who will come as the first one as a domination? Fluorine. Second one will be nothing but which one? It will be nitrogen. Third one, if you compare between carbon and oxygen, then oxygen size is smaller. It will be fluorine, nitrogen, oxygen and carbon. That is IE1. If the electrons are removed, carbon 2p2 it becomes 2p1, 2p2, oxygen is 2p3, fluorine is 2p4, okay, 2p1, 2p2, 2p3, 2p4. Then what will happen? See, oxygen is half filled, stable, okay. So left and right to the stability. Stability wins, then oxygen will become highest. If you compare between 2p2 and 2p4, then 2p4 size factor will dominate and fluorine will have more energy as compared to nitrogen. Then fluorine will dominate. And nitrogen and carbon, if you compare, then nitrogen will dominate to carbon. So it is the order of OFNC. Now if you want, you can remove one more electron and you can compare the IE3. Okay, from 2p1 it becomes 2s2, from 2p2 it becomes 2p1, from 2p3 it becomes 2p2, from 2p4 it becomes 2p3. Okay, so if you compare out of all this, got it? So this is a stability 2s2 and this is a stability 2p3. 2s2 and 2p3, they both are stability, and in between there are two, 2p1 and 2p2. So how to compare? I told you the size factor will dominate between this and this size will be smaller. So fluorine will dominate first. Okay, first fluorine will be there. Second, if you compare between 2s2 and 2p2, between 2s2 and 2p2, so they are not next to each other, they are next to next. So size factor will dominate. So again will come oxygen, and these are present next to each other and stability will dominate. So this will be, first will be fluorine, then will be oxygen, then will be carbon, and then will be nitrogen. So this is how you can compare with this. Okay, next you can you can relate between sodium, magnesium and aluminum, and you can check. One I am going to tell you, the other you can check. It is 3s1, 3s2 and 3p1. Out of this 3s1, 3s2 and 3p1, you tell me which will have more. Obviously this is stability. Stability will be more, magnesium. To the left and here, so between this and this, size comparison, this is smaller, aluminum. Between this, then comes sodium. So rest IE2 and IE3 you can calculate by your own and you can check. I hope you have understood. Next we go on to, so when you go across the period, ionization energy increases. Maximum is for noble gas, and when you go down the group, ionization energy decreases. And successive ionization energy for an element is IE3 greater than IE2 greater than IE1. Electron affinity. Electron affinity. So electron affinity is nothing but the energy released when electron is added to an isolated gaseous atom. So electron is added, so it is an electron, it is a exothermic process and energy will be released. So let's suppose if in X electron is added up to give X minus, delta H is equal to minus EA1. Okay, so if you talk about the reverse of this, X minus changes to X plus electron, delta H is equal to IE1. So what I am saying is, this is electron affinity and this is ionization. So the electron affinity of an element is equal to the ionization enthalpy of its ion. Okay, so period wise electron affinity increases and group wise the electron affinity decreases, and the maximum electron affinity is for non-metals because electron affinity is basically for non-metals. Okay, now next come on to, if you compare across the period from lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. Okay, so lithium, dear students, please remember lithium is an exception to boron and nitrogen. Boron and nitrogen, lithium is exception. So an electron affinity of lithium will be greater than boron and nitrogen. Please remember this is an exception. Okay, it's exception, why? Because it's all coming from thermodynamic calculations. Beryllium there's no tendency to accept the electron. Saturated configuration, electron affinity is 0. Okay, even for noble gases it is saturated, electron affinity is 0. If you compare between nitrogen, oxygen and fluorine, carbon, nitrogen, so carbon is having 2p2 and nitrogen is 2p3. So carbon will have more tendency to gain electron as compared to nitrogen because nitrogen is stable. Nitrogen and oxygen, nitrogen is stable, so more tendency is for oxygen. And fluorine and nitrogen, if you compare, the fluorine is having more electron affinity, while because fluorine is smaller in size. So group, this is what we have come up. This is what the discussion is. Boron is less than carbon. Carbon is greater than nitrogen. Nitrogen is less than oxygen. Oxygen is less than fluorine. If you come on to the group analysis, fluorine, chlorine, bromine and iodine. Normally going down the group, the electron affinity decreases. So fluorine is expected to have the highest electron affinity. Yeah. But contrary to this point, the exception is there. Fluorine is not having greater. So it is 1, 2, 3, 4. The order becomes 2, 1, 3, 4. 2, 1, 3, 4 means 1 means the maximum. Second is the second one. And third, 4. Similarly for nitrogen, phosphorus, arsenic, antimony, same order is there. 2, 1, 3, 4. But extremes order is obtained for oxygen family. It is O 1, 2, 3, 4. But the order is expected as 4, 1, 2, 3. So oxygen, which was expected to have the highest electron affinity, it is having the least electron affinity as here. So as I said, Z cross increases, force of attraction increases, atomic size decreases, ionization energy increases, electron affinity is also increasing, electronegativity is also increasing. If you check between fluorine and chlorine, the size of fluorine is greater than that of chlorine. So this is fluorine, 7 electrons in the outermost, and this is the nucleus. Okay, this is the nucleus and the 7 electrons. Now these 7 electrons, isn't it, they are condensed, they are very nearer to each other. So if an incoming guest is coming, where it will go? Will it go to here or it will go to here? Definitely it will go here. Why? Because the inter-electron, electron repulsions are less. So the electron which will come here, it will have less repulsion as compared to the electron over here. So this is what the order of electron affinity we have discussed. We'll just take a break of 1 minute and we'll get back to you with the further discussions. Next we come on to the discussion of electronegativity. What exactly we mean by electronegativity and what is the difference between electronegativity and electron affinity. So electron affinity is nothing but energy released, while electronegativity is a theoretical discussion. Electron affinity is talked about isolated state, while in electronegativity is talked about combined state. Okay. This is the point of discussions. Electronegativity, when we talk about, it is a tendency to attract the shared pair of electron towards itself. Towards itself, we talk about electronegativity. So when we move across the period, the electronegativity goes on increasing, and going down the group, the electronegativity goes on increasing. Electronegativity decreases down the group and increases along the period. So fluorine will be having the most electronegative. So there is a diagonal relationship also has been observed in the periodic table. 3 groups: lithium, magnesium, beryllium, aluminum, boron and silicon has observed a diagonal relationship. Why this diagonal relationship was observed? Why this is observed? Theoretical discussion we can do once we know that this relationship is observed. Why not it is observed for other groups? This is not a question, because this is not observed. Simple thing is that on the basis of observation only we are just relating the theory. So lithium and magnesium resembles with most of the properties in terms of compound formation, like lithium reacts with oxygen to form oxide, magnesium also reacts with oxygen to form oxide, lithium carbonate decomposes to form lithium oxide and carbon dioxide, magnesium carbonate also decomposes to form magnesium oxide and carbon dioxide. Many other or more properties are there which we can relate. Okay, so what is the theoretical discussion? While going across a period in the periodic table, electronegativity goes on increasing. While going down the group, electronegativity decreases. So the increase of this and the decrease of this will be compensated when you go across the from lithium to magnesium, and that is what the we have come up with the explanation of the diagonal relationship. Even when you go down the group, what we see across the period, atomic size increases, atomic size decreases going across the period, and going down the group, atomic size increases. So going diagonally, what will happen? The decrease and the increase will be compensated, and that is why lithium and magnesium will show a resemblance in the sizes also. Okay, this is what we have discussed about all this parameter periodic table. Okay, next we come on to the part of discussion which we have is adsorption. What is adsorption? Basically, if you see, it is nothing but the phenomena of concentration of molecules of a gas or liquid at a solid surface is called as adsorption. So this is the solid surface, and in this solid surface what is happening? These are adsorbed gas molecule. So the phenomena of concentration of molecules of a gas or liquid at a solid surface is called adsorption. Now, for adsorption to happen, we are talking about adsorbent and adsorbate. What is adsorbent? Dear students, it's clear from here. One which provides the surface is called as adsorbent, and on the surface the one gets adsorbed is called adsorbate. So this is adsorbate, and on the surface, on whose surface action happens, that is called adsorbent. So this is adsorption, deposition at the surface only, while the one thing more is called absorption, and that absorption is nothing but penetration into the body of the solid. So if you talk about the chalk crayon, okay, when you dip that chalk crayon in ink, what happens? What happens? Adsorption happens, okay, because when you break also you will find white from inside. Okay, so example, if you talk about of adsorption, it is adsorption of a dye by charcoal. Okay, so my dear students, when I'm saying under this discussion adsorption of a dye by charcoal, if you have a finely divided charcoal, and if that finely divided charcoal is stirred into a dilute solution of a dye which is called methylene blue, what happens? Can you check what happens? Can you think about it? What happens when a finely divided charcoal is stirred into a dilute solution of methylene blue? The blue color, the depth of the color, of the solution decreases gradually. Why? Because the dye molecules have been adsorbed by the charcoal particles. Okay. Similarly, adsorption of a gas by charcoal. When I say adsorption of a gas by charcoal, okay, for example, if we have a gas like sulfur dioxide, chlorine gas, ammonia gas, and if you treat it with a powdered charcoal, coke means, okay, in a closed vessel, what is observed? The gas pressure is found to increase. The gas pressure is found to increase. Why? Because the gas molecules concentrate on the charcoal surface and are said to be adsorbed. This is what I've talked about, the adsorption. Now if you talk about mechanism of adsorption, if you see here, I have shown you mechanism of adsorption. This is the platinum metal atoms are there. They are having metallic bonds between them. But the dotted ones which I have shown you, they are nothing but called as a residual valence. Okay. So this is hydrogen which is molecularly adsorbed on the platinum, and this is hydrogen which is atomically adsorbed on the platinum. This is all residual valence. So what happens? The atoms or the molecules of a solid surface behave like surface molecules of a liquid. These are not surrounded by atoms or molecules of their kind. Okay. So what they have an unbalanced or the residual attractive forces. Okay. That is how they can hold the adsorbate particles. Now what is the type of adsorption? We have two types of adsorption. One is called physical adsorption. One is called chemical adsorption. Now in physical adsorption, what happens? It is also called as van der Waals adsorption because it is a physical process. And chemical adsorption is a chemical process, means bonding is taking place between adsorbate and adsorbent. And once bonding take place, then nothing can happen. Okay. So this is what we are talking about. So next discussion is of mechanism of adsorption. So what is happening in physical adsorption? The gas molecules or the atoms are held. The gas molecules or the atoms are held to the solid surface by means of what? By means of what? Van der Waals attractive forces. That is why it is called van der Waals adsorption. Okay. Let's suppose adsorption of hydrogen on charcoal. Adsorption of hydrogen or oxygen is taking place on charcoal is what? It's a physical adsorption. Okay. So here, this is what I am trying to show you. This is a hydrogen molecule. It is trying to get adsorbed. So when physical adsorption take place, what is happening? This is hydrogen molecule getting adsorbed. So this is nothing but the residual valence, and between this is a covalent bond, and between this is nothing but van der Waals force. So between this and this is a van der Waals force. Between this and this is a chemical bonding. So once if you increase the temperature, what will happen? The physical adsorption, okay, it changes into chemical adsorption, and the hydrogen molecule is said to be chemically adsorbed on nickel. Okay. So this bond will break. When you increase the temperature, this bond will break. So these bonds are breaking, and this bond will become what? The van der Waals. These bonds will be nothing but the chemical bonding, which I am trying to tell you. Chemical adsorption. So this physical can pass into chemical adsorption, my dear students. Okay, but chemical adsorption never passes into physical adsorption. It has been observed. Okay, this is van der Waals, and that is chemical forces. Next we come on to adsorption of gases by solids. So when you talk about the adsorption of gases by solids, okay, what is important thing? So first point we come into hit is adsorption and surface area. Okay, so by more the surface area, more is the extent of adsorption. Okay, so extent of adsorption increases with what? Surface area. So you can say that what extent of adsorption is directly proportional to surface area. More the surface area, more the extent of adsorption. And that is why, my dear students, finely divided metals, if you think of nickel, platinum, palladium, and porous substances like charcoal and silica gel, they provide a large number of surface area, and that are best solid adsorbent. If you see that silica gel is also provided in the shoes also. Now think about it, why it is provided. Next is nature of gas. As I said, adsorbent we have already talked about. Now we are talking about adsorbate, one who is going to come. So one who is going to come and getting adsorbed, definitely that will depend on the nature of the gas. Okay. So what nature of the gas which we have observed? In general, dear students, more easily liquefiable gas. What is more easily liquefiable gas? The one which has higher critical temperature, the more readily it will be adsorbed. For example, if you talk about, this is a charcoal surface, and in this charcoal surface, 1 gram charcoal surface, if I take 1 gram, then it absorbs 380 milliliter of sulfur dioxide, 16 milliliter of methane, and 4.5 ml of hydrogen. Why? Because the critical temperature of SO2 is 157 degrees centigrade. If you talk about methane, is minus 83 degrees centigrade, and if you talk about nothing but hydrogen, it's minus 20 degree centigrade. So what is adsorbed more? 380 milliliter of sulfur dioxide, because its critical temperature is more, 157 degree centigrade. While chemical adsorption, if you talk about, on the other hand, is very much specific. Very much specific. All the gases are not adsorbed. Okay. Only that will be adsorbed which can make a chemical bond. But physical adsorption, any gas which comes lesser or more, it will be adsorbed. So chemical adsorption is specific, while physical adsorption is not at all specific, dear students. Okay. Next we come on to heat of adsorption. Sorry, actually this will come into nature of the gas, and now we are coming into heat of adsorption. This all discussion which we have done comes into nature of the gas. Okay. Now if you talk about, we can talk about separately about heat of adsorption. What is heat of adsorption? Heat of adsorption is nothing but, I can say, amount of heat liberated when 1 mole of substance is getting adsorbed. Amount of heat liberated, okay, when 1 mole of substance is getting adsorbed is called as heat of adsorption. Got it? So it is an exothermic process. Okay. So in case of physical adsorption, since it is a van der Waals attractive force, the heat of adsorption is very less. But in case of chemical adsorption, as it takes place between the bonding between adsorbate and adsorbent, higher heat of adsorption is observed, nearly 20 to 100 kilocalorie per mole. Okay. But if you talk about the thermodynamics of adsorption, that is delta G is equal to delta H minus T delta S. Okay. So delta H is negative for the adsorption process. Okay. Because the heat is released. Even delta S is also negative for the adsorption process. Both are negative for adsorption process. So delta G also has to be negative. But when delta H and delta S both are negative, then delta G will be negative. Only at what conditions of temperature, dear students? Tell me. When delta H is greater than T delta S. When delta H is greater than T delta S, delta G will be negative. And for adsorption, dear students, it is a spontaneous process. Adsorption is a spontaneous process, because more or less, delta G will be negative. So this is what we have talked about. And as far as next is concerned, that is a reversible character. Yeah, reversible character means physical adsorption is a reversible process, as I told you. Okay, it passes into chemical, but chemical adsorption does not passes into physical adsorption. Okay, so if you have a gas, free gas, this is a free gas, and this is the gas which is adsorbed. So free gas is in equilibrium with gas in solid plus heat. So it is in what? Plus heat means exothermic process. No, free gas minus heat changes to, so adsorption is a, so exothermic process. What is exothermic process? Adsorption is an exothermic process, while reverse will be what? Desorption, which is an endothermic process. So adsorption is exothermic, low temperature will favor it, while desorption is endothermic, high temperature will favor it. Okay, that is why I am saying you, it is free gas is in equilibrium with gas in solid plus heat. Now effect of temperature. What is the effect of temperature? Simple thing, physical adsorption occurs rapidly at low temperature. So this is the graph I am telling you, occurs rapidly at low temperature. Okay, while it decreases with increase in temperature. Occurs rapidly at low temperature. So the graph is, I have shown you here, okay, and it goes like this. Occurs rapidly at low temperature and decreases with increase in temperature. This is physical adsorption. If you talk about chemical adsorption, dear students, chemical adsorption, it has been found to be generally increase with increase of temperature. Generally increases with increase of temperature. So this is extent of adsorption and this is temperature. This is maximum adsorption is taking place at this point. So here the extent of adsorption increases with increase in temperature, goes to the maximum, and later on it has been observed that the extent of adsorption goes on decreasing. Okay, so this is what we have discussed. Next is same as effect of pressure also. Gas is in equilibrium with gas in solid. This is nothing but free gas. So obviously when you increase the pressure, it will cause more of adsorption, and decrease of pressure will cause desorption. Increase of pressure causes adsorption, decrease of pressure causes desorption. That is why we say it is x by m versus temperature at a particular pressure. So this is what it is happening. So this is will reach into what? I'm talking about pressure here. Okay, so it is increasing and it is becoming constant. This is nothing but called PS, and PS you know better than me. It is called as saturation pressure. Got it? So it is increasing with increase, and at this point it reaches to a saturation point, and this saturation point we call it as PS, that is equilibrium point. Okay, so next is thickness of the adsorbed layer. Okay, physical adsorption is a multimolecular, because the gases gets adsorbed and it happens continuously because of van der Waals, while chemical adsorption is a monolayer thick. Remember that. Let's go on to the adsorption isotherm. Whenever the adsorption of a gas on a solid adsorbent, if you talk about in a closed vessel, is a reversible process, dear student. The free gas is in equilibrium with gas adsorbed on solid. So the amount of gas adsorbed depends on what? Equilibrium pressure and temperature. That's what I said. Adsorption of a gas on solid adsorbent in a closed vessel is a reversible process. The free gas is in equilibrium with gas adsorbed on solid. So the amount of the gas adsorbed depends on equilibrium pressure and temperature. Let's see this, how it depends on this. There is a curve called as Freundlich adsorption isotherm. What we call Freundlich adsorption isotherm. What is Freundlich adsorption isotherm? It is nothing but the relationship between the equilibrium pressure of a gas and its amount adsorbed on the solid adsorbent at any constant temperature is called adsorption isotherm. And that is what he has said, x by m is equal to k p to the power 1 by n. What is x by m? Extent of adsorption. What is x? Amount of gas adsorbed. What is m? Mass of adsorbent. What is p? Pressure. So k and n, if you see here, they are constants, and these constant depends on what? Nature of gases, temperature and adsorbent. Nature of gases, temperature and adsorbent. So if you draw the graph, that's what I'm shown you earlier also. X by m versus p, the extent of adsorption increases with increase in pressure, but after a certain point it becomes what? Constant. That point is nothing but called as PS, saturation pressure, and that curve is obtained at high pressure basically. Okay, and that is why we say that Freundlich adsorption isotherm is not able to explain the adsorption of gases by solids at high pressure. Why? Because if low pressure, if you talk about, it will give you a straight line. So just put the logarithm in this. Just put the logarithm in this. So it will give you log of x by m is equal to log of k plus 1 by n log of p. So giving you the straight line y is equal to mx plus c. So these graph is obtained. Okay, where this is one log case intercept and slope is equal to 1 by n. So this is how the slight curvature will be there obtained at high pressure, and the plots were straight line at low pressure. I hope you have understood this particular discussion which is done right over here. Now we come on to next point of discussion, which is nothing but called as a colloids. On colloids we talk about dispersed phases and dispersion medium. What is dispersed phase, dear students? This is a copper, this is a copper getting dissolved in the solvent, you can say. So this copper which is present in small amount, it is called as a dispersed phase, and dispersion medium is nothing but the entire solvent is a dispersion medium. So solid dispersed in liquid are called as sols or colloidal solutions, and this colloidal solution in water is called hydrosol or aquasol. If colloidal solution of alcohol is there, colloidal solution in alcohol, it is called alkosol, and if it is in benzene, it is called benzosol. So just tabular form, you can remember all those things. What is that? Gas in liquid, gas in solid, liquid in gas, liquid in liquid, liquid in solid, solid in gas, solid in liquid, and solid in solid. So dear student, these questions are also examination based asked question. What if you talk about gases dispersed in liquid? Example is foam. What is the type? Means foam. And gases dispersed in liquid, example you can talk about wiped cream, the shaving cream, okay, soda water. All these are nothing but gases which are dispersed in liquid, comes under foam category. Okay. The second one we can say gases dispersed in solid. When gases are dispersed in solid, it comes under solid foam. If you talk about pumice stone, that is used for beautification purposes, okay, and froth, that is all solid form. Third, if you talk about liquid dispersed in gas, they will ask you what is liquid dispersed in gas. That is called aerosol. An example is fog is there, mist is there, cloud is there. All these are discussed in this category. If you talk about liquid in liquid, that comes under emulsions. Emulsion category will be milk is there, hair cream is there, which comes under emulsions. If you talk about liquid in solid, that is called solid emulsion, also called as gel also, dear students. It is called gel also. Butter is there, cheese is there, which comes under liquid solid category, liquid dispersed in solid. If you talk about solid dispersed in gas, what it is called? Smoke. If you see dust, that is an example of smoke. If you talk about solid dispersed in liquid, this is called as sol, which we are discussing about sol, colloidal solution. Solid dispersed in liquid is called colloidal solution. For example, you can talk about paint is there, ink is there. And if you talk about solid and solid category, then it will come ruby glass is there. Ruby glass is a type of glass where gold is dispersed in glass. We talk about two. So we have colloids, that is nothing but colloids is lyophilic and lyophobic. Lyophilic is solvent loving and lyophobic is solvent hating. Okay. So optical properties of sols we are coming up, and this sols, my dear students, this sols exhibit Tyndall effect. Tyndall effect. What is Tyndall effect? If you talk, it is nothing but actually the phenomena of scattering of light by the sol particles is called Tyndall effect. The phenomena of scattering of light by the sol particles is called Tyndall effect. So my dear students, if you have seen the hazy illumination of the light beam from the film projector, if you sit in a cinema hall, the hazy illumination of the light beam from the film projector in a smoke filled theater Or if you see the light beams from the headlights of car on a dusty road, these are familiar example of Tyndall effect. Okay, but if the Sol particles are large enough, they may even appear turbid in ordinary light as a result of Tyndall scattering. Okay, true solutions, my dear students, do not show any Tyndall effect. Why? Because the ions or solute particles are very, very small to scatter the light. Okay, so if you pass a light and if you view the beam of light passing through a true solution, then it is not visible. The light is not visible when it is viewed from the side. But Tyndall effect can be used to distinguish between a colloidal solution and a true solution. So if you are passing a light beam from this side, if you are passing a beam of light from this side and you are seeing it from here, then the light beam is not visible, and this will happen in case of true solutions. If you are passing the same light beam continuously from this particular, okay, and you want to see from this the light beam becomes visible. So when the light beams are becoming visible, this is called as colloidal solutions, and when it is not visible, it is nothing but called as true solutions. Okay, now important properties we can discuss about optical properties. There are again kinetic properties of the colloidal solutions also, like Brownian moment is also there. You can have a study of it. That is nothing but the continuous rapid zigzag motion, okay, by the colloidal particles is there in the dispersion medium. It is called as Brownian motion, or the motion only, you can say. Okay, this is called colloidal Brownian motion. And if you talk about the electrical properties of the Sol particles, they carry an electrical charge. The Sol particles, they carry an electrical charge. How they carry an electrical charge, that is what I am showing you here. See, these Sol particles, if you show here, or I am just trying to show you here this particular diagram, this is nothing but a positively charged colloidal particle, and these are nothing but the positive ions which are adsorbed on Sol particles. So they are under repulsive forces. Similarly, you can say these are again positive charge, and these are positive ion, okay, adsorbed on Sol particle. So what is a Sol particle? This is Sol particle, got it? These are Sol particles, colloidal particle, and these are the positive ions and they're put under what? They're put under dispersion medium. They're put under dispersion medium. So in the dispersion medium, we have counter ions also. So like negative ions are there, negative ions are there, negative ions are there. All these are negative ions. So adsorption of ions from dispersion medium. So these adsorption of ions, when you're putting in the dispersion medium, the adsorption of ions from the dispersion medium gives charge to the Sol particles. And due to that, they are not settling down on account of mutual repulsions. Okay. So what I'm saying is, the mutual forces of repulsion between similarly charged particles, this prevent them, okay, from aggregating and settling under the action of gravity, and this gives stability to the Sol particles. Okay. If you talk about why a ferric hydroxide Sol particles is a positively charged Sol particle, because ferric hydroxide adsorbed the ferric ions. It absorbed ferric ions. From where it is absorbing ferric ions? From the ferric chloride. It is absorbing ferric ions from ferric chloride, and therefore this ferric ions, they are on all the sides, they are getting adsorbed because of the common ion, and this is how adsorption is taking place. And the charge on the Sol particle is counterbalanced by oppositely charged ions termed as a counter ions. So when counter ions are there, counter ions are what? Negative ions. So when these are there, similar charge particle, it is not allowing them to settle down. When counter ions will be there, they will allow them to settle down. Okay, this is what we observe. Okay, so just remember, we have a negatively charged something is called we have negatively charged, and we have something positively charged Sol particles. Like ferric hydroxide is gonna to be a positively charged, aluminum hydroxide positively charged, hemoglobin also, if you talk about, it is gonna to be a positively charged, while negatively charged, if you talk about metals, are negatively charged. Example, gold is a negatively charged, platinum is negatively charged, we have arsenic sulfide As2S3, we have starch is a negatively charged, we have clay is a negatively charged. All these are negatively charged and all these are positively charged particles. So there is an important term, I hope you have understood what I wanted to discuss. So now I'm talking about a term called coagulation or precipitation. So what is coagulation or precipitation, dear students? Actually what happens, the stability of the lyophobic sol is due to what? Tell me. It is due to the adsorption of the positive or the negative ions by the dispersed particles. And this repulsive force between the charged particles, they do not allow them to settle down. Okay, so if somehow the charge is removed, what will happen? There will be nothing there to keep the particles apart from each other. So they will be aggregating and they will be settling down under the influence of gravity. So this is nothing but called as precipitation. What? The settling down of the charged particles. So this settling down can be done, or precipitation can be done by 4 ways: by addition of the electrolyte, by boiling also we can do. For example, let's suppose this is a vessel and we have a lot we have here as a dispersion medium is there. Okay, so here we have negative ions are there. Remember, these are negative ions are there, all negative ions are there. Okay, so what we are adding now, we will add sodium plus, this is added to negative sol. When you add sodium plus is added to negative sol, what will happen? You know, this will become neutral now. So this all will become neutral because already this is a dispersion medium. This all will become neutral. So this all has become neutral. Now what will happen? This neutral particles, what they will do, you know, they will be segregating with each other, and this segregation and settling down is nothing but called as coagulation. So these are nothing but settling down and under the influence of gravity, and this is nothing but called coagulation. So a negative ion, so this is nothing but called discharged sol particles, and this is called coagulated sol particles. These are discharged sol particles and they are coagulated sol particles. So what we have observed is a negative ion causes precipitation of a positively charged sol and vice versa. And this is nothing but has been given in terms of a rule called as a Hardy and Schulze rule. Hardy and Schulze rule, what they say that the higher the valency of the effective ion, the greater is the precipitating power. So if you want to precipitate As2S3, that is a negative sol, the precipitating power of aluminum, barium and sodium will be in the order of this. So more the valency, more is the precipitating power. So a negative ion will cause the precipitation of a positive and vice versa. Similarly, if you want to precipitate a ferric hydroxide, which is a positive charged sol, then the precipitating power of FeCN, the whole 6 minus 4, and that comes next is we can talk about sulfate is there, Next thing you can talk about chloride. So this is -4 charge, -2 and -1. So in order to precipitate this, this is having the maximum power. This is called as Hardy and Schulze rule. And along with Hardy and Schulze rule, there was one term discussed called as a flocculation value. So remember, what is flocculation value? I'm just speaking up with the flocculation value definition. You just check and remember that. This is experimentally determined actually. And what is that? The precipitating power of an electrolyte or ion is experimentally determined by finding the minimum concentration in millimoles per liter to cause the precipitation of a colloidal sol in 2 hours is called flocculation value. So smaller the flocculation value, greater is the precipitating power. Smaller the flocculation value, greater is the precipitating power. So FeCN the whole 6 minus 4 is having a smaller flocculation value. This is what we have discussed about the properties. Next we are coming up with an important thing, which is nothing but called as a gold number. What is gold number? This is very important, asked in the examination. Gold number. This is actually, we are measuring the protective power of the colloid, and that protective power of the colloid is defined for lyophilic colloid. What is a lyophilic colloid? That is a protective colloid. Okay, and what we are doing for the protection, see here. Number of milligrams of protective or lyophilic colloid added in 10 ml. So here we have this particular which we have talked. This is nothing but 10 ml. This is 10 ml gold solution, which is a lyophobic. Lyophobic is there, solvent hitting. As we have lyophobic means which does not dissolve easily, dear students. Okay, but lyophilic, they dissolve easily, like gum is there, starch is there, they dissolve easily, therefore they are lyophilic. Easily one who dissolves is lyophilic, and which does not dissolve easily, they are called lyophobic. So we want to measure what? So these are nothing but 10 milliliter gold solution, they are called lyophobic. And you are adding 1 milliliter NaCl, which is nothing but concentration is 10% weight by weight or weight by volume, which is given here. Number of milligrams of protective or lyophobic not added in 10 ml to stop coagulation. Okay, so when you add I hope you are understanding it. Okay, so this is 10 milliliter gold solution. So you are adding what? 1 milliliter of NaCl, 10%. Okay, now in order to prevent the coagulation, when you add this, this will get coagulated. Gold solution. When you add this, this will get coagulated. In order to prevent the coagulation, what we are adding? What we are adding is lyophilic colloid. This lyophilic colloid will prevent the coagulation. So how much you add? You are adding X milligram. So X milligram of lyophilic colloid is added in this particular to prevent the coagulation from this 1 milliliter 10% NaCl solution. Okay, on adding NaCl to gold solution, coagulation take place. That is what I am telling you. So to prevent coagulation, lyophilic colloid is added. Okay, how much you are adding? X milligram. So whatever you add X milligram, that is called as gold number, because it is defined for 10 milliliter gold solution. So we can say gold number is nothing but number of milligram of protective colloid divided by volume of solution in milliliter into 10, because it is defined for 10 ml. So let's suppose if you add 2 milligram of lyophilic colloid in 10 milliliter gold solution. If you add 2 milligram of lyophilic colloid in 10 milliliter gold solution, then the protective power gold number will be equal to 2. Okay. For example, if you are adding in 100 ml solution, what? If in 10 ml gold solution, you add 2 milligram of lyophilic colloid, Then in 100 ml, you need to add what? 20 milligram. That is called as gold number. Okay. So what is defined? So for 100 ml, let's suppose our solution is given 100 ml and 20 milligram you are adding protective power X. So for 100 ml, if it is added 20 milligram, then for 10 ml, how much is added? 2 milligram. So 2 milligram is nothing but called as what? Protective power of lyophilic, which we are adding, that is gold number. So what has been observed is protective power is inversely proportional to gold number. For example, we have two, A and B. Gold number is 10 and 20. Now which has more protective power? So this 10 can prevent the coagulation. So this has more protective power. Lesser is the gold number, more is the gold number increases, protective power decreases. So 10 is gold number, lesser is the gold number, more is the protective power. That is what I have told you, just a question. If 20 milligram of colloid is added in 100 ml gold solution to stop coagulation, what is the gold number? So for 100 ml you added how much? 20. For 10 it added 2. So 20 by 100 into 10 is 2. That is called as what? Gold number. So this is what we have defined about surface chemistry, colloids, about this. Gold number is very, very important, dear students, and Hardy and Schulz law is also very, very important. Please remember all this. Now we are just going for little discussion into isolation of elements, that is for silver and mercury, silver and gold. We are talking about extraction of silver and gold. There is a famous process called as MacArthur-Forrest process, and that is asked in the examination. MacArthur-Forrest process is used for extraction of silver and gold. So what we do, both the metals are extracted by hydrometallurgy, okay, that is by leaching process. And what we do is we get the ore containing native metals, okay. Native metals means free form. It is available in free form, not in the combined form. And what we add in this, we have 0.4% to 0.6% aqueous solution of sodium cyanide is added. Where? In the ore, because that ore is not pure, it has impurities also. So we are adding 0.4% to 0.6% aqueous solution of sodium cyanide. So what will happen? See, this is a silver, which is an impure silver or ore, we can say that. You are adding sodium cyanide. Along with that, you are adding some water and oxygen. So what it forms? It leads to the formation of a complex, my dear student. So this is converted into complex part, that is sodium dicyano argentate, NaAgCN the whole 2. This is very important. They ask complex here, and 2 NaOH will be formed. Okay. So this impure silver or ore is converted into what? Complex. And whatever impurities are there, it will settle down, will be left behind, and you can filtrate it. That is what I mean. So this complex is important. Remember that in the silver. Same way you can talk about gold also. Same to same process. Just remove silver, you put gold. Okay. Rest remains all things same. So there the complex was NaAgCN the whole 2. Here the complex will be NaAuCN the whole 2. Auric complex. It is also soluble complex. Okay, so whatever the ore containing impurity, gold, it is converted into what? Soluble complex, and the impurities are left behind. Okay, so this is how we can remove the impurities from the ore. And what you do, you filtrate it, and after filtration, you treat it with zinc metal. Why? Zinc metal is more electropositive, and that is helps in the displacement. Okay, so this NaAgCN the whole 2 complex, you add zinc, which is more electropositive. So what will happen? Zinc will displace silver from here. So we get pure silver from here, and we get a soluble complex of sodium tetracyano zincate 2. Same thing we get for gold also. So this is what we are talking about, extraction of silver and gold by MacArthur-Forrest process. This is asked in the examination. Now this is after we get silver, what we do? Refining of silver we do. And how it is refining of silver is done? In the refining of silver, the main impurity present is of lead, and zinc is the impurity. The main impurity is of lead. So there are two ways. One is called cupellation. So they will ask in the examination, cupellation is used when in the silver the main impurity is present as lead. Okay. And electrolytic refining is used when other impurity is there, zinc. So what we take is anode as we take as impure silver, cathode we take as a pure silver, got it? And electrolyte we take silver nitrate, and along with it we take nitric acid. Why we take nitric acid? Because the dissolution of lead is easy when you add nitric acid. So lead will dissolve in nitric acid to form lead nitrate. Similar we do in terms of gold also, electrolytic refining. Anode we are making impure gold, cathode we are making pure gold, and the electrolyte we are taking as aurum trichloride and hydrochloric acid. Next we come on to the metallurgy of aluminium. See, when you talk about the metallurgy of aluminium, we have the ore that is impure, that is a bauxite ore we have. In the bauxite ore is Al2O3.2H2O. What we do first is concentration of the bauxite ore. Okay, so we have alumina. Okay, we have in bauxite ore, we have a bauxite ore, got it? Impurities are present. Okay, depends upon the type of the impurity. If you have a Fe2O3 impurity present in the bauxite, it is basically red in color, that is called red bauxite. And if you have a SiO2, silica as an impurity, then it is called white bauxite. And what we want to do from the bauxite, we want pure alumina. We want pure alumina, that is Al2O3, by removing the impurity. You just remove the impurity and get the pure alumina. So we have three processes also here. Importantly, they're asked in the examination, called as Bayer's process, Hall's process, Serpek's process. Bayer's process and Hall's processes are used when Fe2O3 is used as a main impurity. Okay, it is a leaching process actually. Serpek's process is used when silica is used as a main impurity. Okay, let's see what happens here. You take you talk about Bayer's process. You have an impure ore, okay, that is alumina. You talked about bauxite ore, and you digest it with NaOH. Digest means you make a reaction with NaOH and leave it for 10 to 12 hours, like that. So Al2O3 is there. It reacts with NaOH, forms sodium meta-aluminate along with H2O, and this sodium meta-aluminate formed is soluble in water. And what you have here, you have pure alumina plus impurity of Fe2O3 and SiO2. So Fe2O3 is present as a main impurity here. Okay, so insoluble impurities will settle down at the bottom. That is what it is talked about. Bayer's process, you are reacting with NaOH, you are digesting with NaOH, and this sodium meta-aluminate which you got, you extract with water because we want to get pure alumina. You extract with water. So when you extract with water, you get a hydroxide precipitate, and that aluminum hydroxide will precipitate down. And after the precipitation, you take the filtrate and you heat that aluminum hydroxide at a temperature of nearly 1500 degrees centigrade. So what will happen? Al2O3, you get it, that is pure and dry aluminum. That is called as Bayer's process. I hope you got it, everybody. Next is we have Hall's process. In Hall's process, what we do is we take Fe2O3 again as a main impurity, but the difference is only that there we used NaOH, and here the ore is treated with sodium carbonate, means fusion is taking place. So you treat with sodium carbonate, sodium meta-aluminate is formed, and carbon dioxide gas is released up. So this is soluble complex. Impurities are there. So this sodium meta-aluminate is again, you hydrolyze with water, aluminum hydroxide, same thing is there after that. Precipitate is done and you heat the precipitate here, filtrate, 1500 degrees centigrade, you get pure and dry aluminum. Now we have a Serpek's process used when SiO2 as a main impurity. What you do, you take alumina and you add coke and nitrogen. Coke is carbon, impure alumina, and you add coke and nitrogen. Treat for 1800 degrees centigrade, you get aluminum nitride along with carbon monoxide. Carbon monoxide is poisonous, you know that. So now the impurities are also there. So we need to remove the impurity by reacting with carbon. So silica reacted with carbon, okay, and it forms silicon plus carbon dioxide. Basically this is a redox reaction because silica is +4 changes to silica with 0 oxidation state. And the aluminum nitride which is formed, we actually don't want aluminum nitride, we want alumina. So aluminum nitride is hydrolyzed with water. When it is hydrolyzed, you get aluminum hydroxide as a precipitate, and ammonia gas is also released. And this again, we have done this aluminum hydroxide, you treat at 1500 degrees centigrade to get pure and dry alumina. Okay, so this is what we have talked about. Now we are not going into the refining of alumina. Electrolytic refining is also there. After electrolytic refining of alumina will be done, that you can study by yourself. We have talked about the famous process. This is asked in the examination: Bayer's process, Hall's process, and Serpak's process. And a little more is there in the isolation of elements. You can study that isolation of elements. Theoretical chapter is there. More of theory is there. So more of retention you need to do with the name process. Earlier chapter, what we have discussed is solid state. It is basically 3-dimensional visualization based. So nothing is there to cram. You need to understand the dynamics of solid state and the type of questions we have discussed, and more practice you can do related to that particular chapter. Definitely 1 to 2 questions definitely come from solid state, and 1 to 2 questions comes from periodic table, whatever we have discussed. Surface chemistry is also important with respect to whatever we discussed: gold number and the Hardy and Schulze law and the Freundlich adsorption isotherm. So please don't leave that particular chapter. 100% question is going to come from that particular aspect which I have discussed. And isolation of elements, few things I have discussed about MacArthur or Forest process and the extraction of this aluminum, that is bauxite, from that. Electrolytic refining is again left up. You can discuss, you can read up electrolytic refining, and you can again read some isolation of elements of other elements also. Okay, a lot of time is there with you. You can utilize this time effectively. Okay, silently, coolly, calmly, and discuss as much as question as you can do. And then if you have a certain doubts with you, you can always post doubts. I'm there to solve your doubts. Okay, so remember, take care of yourself for today. Bye bye, and revise again whatever we have discussed for today's thing, and solve as many as questions as you can do. So bye bye students, goodbye for today's now.